So I just gave you a peek, but don't share, okay? Because you are here early, you are here on time. So don't share with people who are gonna show up 15 minutes before. Okay, so we look at this here, which is called a static equilibrium. So I just want to make sure you know how to do it. In that case, it's very easy because this angle here is the same as that angle there, which means that this tension here in magnitude will be the same as this one. But I cannot call it by the same name because they don't have the same direction. And a vector has a direction and a magnitude. And so you need a force here. So if you add them here, you can use a parallelogram or you can use tail to head. You need a force here opposite. So it should be in blue. Okay, so that will be your weight. And the weight is like 4,000 Newton. And the mass here is 400 kilogram. Okay, so don't confuse both. This is inertia, laziness, and this is your weight. Okay, and then you have three ways to do it. You can use geometry. Okay, so you see that this magnitude here, your weight, you see your weight has to be geometry. You use geometry, so that will be 1 and 2. It's a parallelogram, right? So it will be 2t cosine 40. Okay, only in this case when one of the vector is along the vertical. So that will be way number 1. Way number 2 that you're going to use for everything else, you use the components. So this one has a x component, this one has a y component. Okay, and you see this one has a y component and this one has a y component. And then you can use my way. Everything up has to be equals to everything down in a static equilibrium, even in a dynamic equilibrium, which means no acceleration. And if you do it this way, you have to use the magnitude only. Okay, there is no sign. So you see that the y component of T1 plus the y component of T2 has to be equals to 4,000. And those two components are equal to each other. So I can say 2t. The component here will be cosine 40 equals 4,000. Now, if you are still using the sign, you can say 2t sine 50, right? It's the same thing. The angles, this angle here and that angle there are complementary, so it will give you the same thing. The third way you can do it will be the very long way, but you can do that, right? You can find T1, T2, the weight, okay? They have X component and Y component, and the sum of all those vectors has to be equal to 0. So the sum of the X component equals 0, the sum of the Y component equals 0, which in this case, you need to have the negative sign. And you will get the same thing. Is that clear? Okay. So I wanted to review this. You have three ways to do it, right? That will be the long way, the book way, but you can do it this way as well. Remember, test number 2 will be November 14, and it will be everything Newton. So that will be another typical question for static equilibrium. For those who came, here we have chocolate for you, just for showing up. So this is also an equilibrium that will be the weight. And this is very important if you go to civil engineering. You see the weight, that will be the weight here. So if you want to do it geometrically, you see that you need to cancel the weight. So T1 in magnitude, you see T1 plus T2, okay, plus the weight equals 0. So T1 plus T2 equals minus the weight. So that should be the weight here. So if you use the parallelogram, so I'm going to try to make a parallelogram. So that will be parallel to this. That's going to be parallel to that. So it means that's going to be my tension here. T1 will be my tension here, and that's going to be T2. And it makes sense that T2 will be larger than T1. Okay, so if you touch it with your finger, this one will be more tense. Okay, and this one will be less. Okay, so then you have different way to do it. You can use geometry as well, right? You can, let's say you always have this angle here, for example. Okay, so you see that the y component of T2, it's the one in charge of balancing out the weight. Okay, so that will be the y component of T2 here, and that will be the x component of T2. So you see, up, if I do up equals down, okay, you see that the y component here, the y component equals to the weight. So that will be T2, and that will be your adjacent. So that will be a cosine equals to the weight. Or you can do it the long way. Now you see that right equals left. Okay, so what is pulling at right? It will be T1 equals the x component of T2. You see you have a parallelogram, so that will be the sine T2 sine. Okay, so you have two equations. And so from here you can find T2, and once you have T2 you can find T1. Is that clear? So if you go to civil, that's, you know, they always start with that, right? So if you are in the Smokies, in the Smokies we have very unfriendly they have to be very careful with them every year. I mean, the secret is not to go hiking in June or May, because that's when they wake up and they are very hungry and nothing grew yet. So you have to go end of July, August, because they are so full, they're not going to go after you. But every year, you know, every year there's people who get chew on. So anyway, the trick is that you have to hang a bag here, right, with the food. And you will notice you don't want that to be too tense, because it will always do this way. It cannot be otherwise, because the weight down here has to be balanced out by the y component of the tension, T1y and T2y. And if you insist to make it too tense, it's gonna break. Okay, you need enough y component here to balance out the weight. Okay. Okay, so static equilibrium. So in that case, you see, it's not the same tension. The tension here will be larger. So in that case, you need to go with two equations with two unknown. Okay, so for example, if you have 300 here, you see 300 here has to be equals that way. It will be equals to T1 plus T2. And if you make your parallelogram, you see that T2 will be smaller than T1. So this one will experience most of the tension. But now you have two equations with two unknown. That's when you want to use your TI. Because we have TI, so why not using it? So a lot of applications. So for example, what is called rope climbing. You see here, as the weight is going to increase, the weight is going to increase, so this angle is going to decrease. So you can provide more Y component of the tension. And then when you buy this, there is always, they always tell you what's the maximum weight. Okay, so you need to have some engineering to find the tension. Once you have the tension, you have to find the Y component. Once you have the Y component, you know how much weight it can support. So in that case, she will be in static equilibrium. The weight is down, and then that's the tension. And then here, that will be the normal force pushing on the surface. The surface is pushing back, and that will be static friction. Okay, so you need some static friction. So you need those very expensive shoes. And sometimes they put some powder as well. And then they put powder on their hands to increase the friction. Any question? Okay, so here's another example. See, he is in static equilibrium. So you have the weight down. So it's push on the surface. But that here, it's not showing you. But actually, sometimes if you take a class in mechanical engineering or civil engineering, they call that the reaction force. But it's actually it's component of this reaction force. It's just the normal force here, and here the static friction. But sometimes they combine that and they say, oh, that's a reaction force R. It's just connecting to engineering. And then here you have the weight, and here also it's going to be two components here. You have a normal force, which is not the same, and static friction here, which is not the same. It depends on the materials in contact. And then you will say up, up, up plus up equals down, right equals left. So if you do it this way, the mechanical engineering class will be easier. Okay, so example of applications will be pulleys. So pulleys are machine, and machine are here. We have chocolate, but you can use the code. There is a special code to see what you like, like milk or whatever. So anyway, machine are here to make your job easier. So a machine can do two things. Either it's a force multiplier, so it makes you stronger. We call that the mechanical advantage. So if the mechanical advantage is 3, it makes you 3 times stronger. Okay, so the effort will be 3 times less than the load. Or it could be a distance multiplier or a speed multiplier. But you need a trade-off because there is no free lunch. Okay, so if you are doing biking, for example, if you are in low gear, okay, you're gonna make it up slope, but you have to go like this. So it's always a trade-off. So let's take a very easy example with pulleys. So what do you think? So that will be the load. So it's called the load, 1000 Newton, 100 kilogram, 200 pounds. So how much you're gonna have in each of those? 500, very good, right? What's your name again? Vladimir. Yes, yes, yes. So you see, again, the secret can be confusing. So we suppose the pulley is massless. So you're gonna have 1000 Newton here, and then 500 here and 500 here. So we don't care what's going on in the outside world, okay? We just look at the system and what is it touching it? Mother Earth pulling down and those two ropes. So that tension is going to be transferred. So she will have to push with 500 Newton. It seems to me that it's still heavy, right? Because that will be 50 kilogram, 50 is 100 pounds. But then she can use her weight. I don't believe that she can pull this. But anyway, yeah, it sounds very difficult. 100 pounds like this. Okay, so anyway, that's the idea. Now let's take this system here, 100 Newton. How much do you think there will be? So how many pull? Huh? How many do you see touching? Okay, so that will be your bag. We focus on the bag. The bag has a weight of 100 and there is one hop pulling up, one hop pulling up, one hop pulling up. 25 in each will be the first step. And then you follow through, follow. Okay, the effort will be 25 Newton. The load will be 100 Newton. So the mechanical advantage is 4, ideally. This is ideally. Yes, so 1/4. The truth is that you're going to have friction. So there is a threshold that, anyway, it's not going to get better, right? Because friction will add up. Friction adds up, okay? But there is a price to pay because there is no free lunch. We have chocolate today if you want, guys. Occasion, I'm just happy today. No occasion. Yes, that will be my last year teaching, so I'm not so happy about it. But anyway, so if the load moves 1 meters, right, the price to pay is that you will have to pull 4 meters. Okay, that will be the price to pay. So it's like when you are changing your tire, of course you can lift your car, but you need to keep push. Okay, there is a trade-off. Isn't that interesting? So here you have a pulley, and that will be showing you the distance. You have 1, 2, so you have to move 2 units of distance, but your effort will be the load divided by 2. Okay, there is no free lunch. And here, same thing. 1, 2, 3, 4, 5, 6, 7, 8. Mechanical advantage is 8. Effort is load divided by 8. But you will have to pull 1, 2, 3, 4, 5, 6, 7, 8 units of distance. Okay? So these are called machine, right? Okay, same thing with the inclined plane. Will be very heavy. For example, if you have 500 Newton, so 500 Newton is 50 is 100 pounds. 100 pounds, if you have to lift it up 1 meter, it's very hard. But if you make a ramp with a distance equals 2 meters, now you only have to push to 50 Newton, which is like 50 pounds. No, what did I say? Forgot. Yes, 50 pounds. Like 50 kilogram is 100 pounds, so 50 pounds. Okay, so the load will be divided by 2, but you have to push over a longer distance. So that's how they say pyramids. You know, they build the pyramids with inclined plane. Now, yeah, this also very famous. It's called Archimedes screw. So if you want to bring water uphill, not that you have a lot of hills in Holland, It's it's not famous for its mountain like Switzerland, but but they build those amazing dams, you know, they make it livable. So if you want to pull, I mean to bring this water up, you're gonna use an inclined plane. So it takes more effort. Okay, so let's do this one. This one is super easy, extra easy. So you can do it very quickly. Just, so this is like, oh, so what's going on here? It's someone who broke their leg. And so you want to stretch the leg so the bone come back together just the right way. So you have to pull on the leg. Okay, so this system is pulling on the leg. So you have 22 Newton here. That will be 22 Newton there because everything is transmitted at the same rope. So 22 Newton. So it's an equilibrium. So here they focus on the pulley. Okay, so because the pulley is stretching the leg is pulling back the pulley with the same force. For every action, there is a reaction, okay? I've seen the horrible documentary from China. Those people, they want to be taller for some reason. It's not convenient to be very tall, telling you that. So anyway, so they cut the bone, here, and then they apply constant stretch. So it doesn't come back to the, right? You make the face. Yeah, but they do that, right? So they cut the bone and then they bring the bone very close to each other, but not too close, right? They keep stretching on it. So new bones will build back, but it causes a lot of issues, osteoporosis on the long, many side effects, right? Go figure. Okay, so you don't want to do that. So X and Y, short is fine. So you can do it the easy way. You can do it like in your head. T1 and T2, you can make your parallelogram. Or you can say right equals left. So right, everything to the right equals everything to the left, right? So what is pulling? So either you do it geometrically, okay? You see that that force will be F, which is 2 times T1 cosine. Or you say that the x component of T1 plus the x component of T2 equals to F. You can do that too, right? Or you take your parallelogram here, you have your diagonal. See, you cut in half, so this distance here is just 2t cosine 35. Any question? Okay, so the tension is the same, so we're going to have 22 cosine 35 times 2 equals F. Now, if you want to do it the long way, no problem, okay? You can say the sum of the x component equals 0 and the sum of the y component equals 0. So you have to find the x component of T1 plus the x component of T2 plus the x component of F. F will have a negative component equals to 0. You can do it this way. So you have 3 ways to do it in this case. Any question? Okay, so what if we have this kind of problem? So this kind of problem that will be typical for mechanical engineering, but not everyone is going into mechanical engineering, so I'm not going to go into details here. I'm just showing you how to do it. So you have your free body diagram. Okay, and then you can say again, everything pulling to the left equals everything pulling to the right. Okay, that's one way. What is pulling to the left? Can you see that will be the x component of T1? Do you agree? Okay, so either you do it the long way and you say, okay, that will be cosine 90 plus 10, 100, or you can say sine 10. Okay, it doesn't matter. You can say T1, and that will be the sine. So sine 10, which is the same thing as cosine 100. Very good, right? Because they are complementary. And then to the right, I will have T2 here, right? So it will be T2. So T2 cosine, so it will be a sine 80 or a cosine 20. 10, thank you. Okay, so that will be my first equation. And then you can say everything up equals everything down. So what is up? You have T1 cosine 10 equals down. You're going to have the weight plus sine 10. So this is in magnitude. Make sure and that will be a T2. So make sure you do not have, if you do it this way, make sure that here you do not have any negative signs, just the magnitude. Okay? And then physics stops, and then algebra takes over. So the other way to do it is this way. You will have to do the x component plus the y component. The x component here, all the x component add up to 0, and all the y component add up to 0. So you still get two equations with two unknown. Agree? So either you pull your hair and you do substitution, or you know how to use your TI that you pay like $80 to $100, so you better use it. You better learn how to use it, and you put that in a matrix. It's like easy linear algebra, and you solve. If you pay that much, you have to use it, right? So this is the boring way, substitution, and you find the answers. You can do it on your own, especially if you go into mechanical or civil. You want to make sure you know how to do it. Here, there is another example. Still, you're going to come up with two equations with two unknown, right? I'm not going to do it, but I show you when you have the two equations. You see one equation here, you have equals to 100. You can use your TI, and the TI will give you the answer. So I'm not going to do it, but I have a YouTube video here that someone did to show you how to solve those problems and how to use your TI. So you don't have, like, if you have a mathematics class, you really want to know how to use your TI. You have different way to use your TI for that. How to solve two equations with two unknown. You can use linear algebra. You can do it if you have more than two unknown, right? You have to make a matrix, you see, 2 rows and 3 columns, and it's easy. We keep that for the assignment. If you go to mechanical, I highly recommend that you do it. A lot of applications, so that was very in the fashionable. I don't even know how to say that name, but it came in the 60s. Well, it seems like to be magical, but actually it's all about tensions. And if you add all those tensions together in a vector sum, it goes to 0. And if you are in architecture, it's explained here. And then they have kits that you can buy online. Here. So it's crazy, right? You have the weight pulling down, and then if you add those all the tensions there, and the weight and the normal force, It's very strange, but it works, right? You can build that for a demo, boom. Super cool. Especially if you are into engineering. Okay, so now the elevator. So do remember two things. I keep repeating it, is that don't forget to take a chocolate or two before you go. The first thing is that the normal force is your apparent weight. How much the surface, the ground, at least when it's the ground, is pushing back on you, or the wall, could be the wall as well, right? How much is pushing back on you, that will be how much you are, how much weight you feel, right? It's like a support force. So the normal force is always the apparent weight. Second, if you have an acceleration, that means you have a force, a largest force in this direction. You need a winner in the same direction as the acceleration. So sometimes it's not that obvious. And the third thing is always look at the system. Are you focusing on the on that person inside, or are you focusing on the elevator? And you put your elevator in a bag and you don't care what's going on inside. Okay, so it's not the same. So let's try to do this one. You can try to do it, okay? So what does it say? The acceleration is 2. The person is 800 Newton, 160 pounds. And the question is, oh, what is the apparent weight? Okay, when they say what weight does the scale read? So his or she is standing on the bathroom scale, so she will read her or his apparent weight. So the apparent weight is the normal force. So basically, they're asking you to find the normal force. So the mass, they say the weight is 800 Newton of the person. Yes, the mass is 80 kilogram. So the acceleration is up, and the acceleration is 2. Guys, they do the free body diagram, but that will be your job to do it. You have to understand that the normal force has to be larger than the weight. Otherwise, it will not accelerate up. You need a force to provide the acceleration, right? So remember, acceleration is proportional to the net force. So you need a winner. You can say like up is winning, right? So winner minus loser equals mass times acceleration. Acceleration is up, you need a winner. No, the question is find your reading on the bathroom scale. So up will be, we don't know, up will be the normal force, right? We're going to find out. Oh, you did find it. Minus, oh, sorry, minus. So N is the winner, minus. So minus 800, right? Times inertia, 8 times 2. So the normal force will be 800 plus 160, which means that your apparent weight has increased by 160 Newton. Agree? That makes sense because you see you have to accelerate. So the floor here is pushing you up. So the bathroom scale is going to read more. So normal force will be 860 Newton, which will be your apparent weight. Yes, you're right. Uh, 9. Okay. So if you want to find how the percentage up, so typical engineering question, so you have increased your weight by 160 relative to your original weight, which is 800. So that will be the percentage increase. Yes, very good. 20% increase. So your weight increased by 20% and your stomach, it's gonna feel like this, right? These are butterfly, if you don't see what it is. Butterfly in the stomach, okay? Because the stomach has like a sensor inside, okay? So if you are asked to find your apparent weight, the apparent weight is the normal force, right? You push, the floor is pushing. So the normal force has two jobs, to provide the acceleration and to balance out the weight. And now let's do the opposite. Now you are accelerating down. Okay, so try to do it accelerating down. Same acceleration down, right? So it's negative. So I like to take plus along the acceleration. So you that way you don't do any mistake. So now which one has to be larger? Weight, very good, right? The weight. The weight is the winner. The weight has to be larger. So you're gonna feel very light. Okay, so you're gonna have winner, so down, minus loser equals mass times acceleration. So the weight will be, what is the weight? 800 minus the normal equals 160. Okay, so now the normal force will be 640 Newton, and that will be your apparent weight on the bathroom scale. Okay, and again you lost 160 Newton out of 800, which again is 20%. So you lost 20%. So we can make a scheme, right? We're going to make a startup. You say, okay, we guarantee you're going to lose weight like this. We put them in an elevator. They look, we fill out the contract, right? You lost 20% of your weight. Yes. Okay. Any question? So sometimes they try to trick you, right? And in that case, they will have an elevator here and some people inside. But now they ask you to find the tension here. And let's say the acceleration is still a. So in that case, you don't care about what's going on inside. Okay, you don't care about the normal force. It's private, right? Let's give them privacy here. That will be a bag. And in that case, you're gonna say, okay, there is a weight. So that tension better be larger than the weight, and that weight has to be the weight of the people plus the weight of the elevator, right? So in that case, you have the tension from the cable, and here you have a motor, and minus the whole weight, I don't know, big M G equals the acceleration. Okay, so that will be including the elevator plus the people inside. Okay, so you have to decide what is your system. Okay, what is it that you put inside your bag? Okay, so you can do the experiment in an elevator. So if it's going down, the weight here down has to be larger than the normal force. So you are not pushing as hard. So your reading will be less. You feel lighter. Okay, something to remember, the net force, okay, is proportional to the acceleration. So for example, if you are in free fall, okay, your acceleration will be 22 miles per hour per second. That will be 10 meters per second per second. If you are 100 pounds, that will be your same acceleration. But nature doesn't know if you are falling or moving along a straight line, which means if someone push you, because it's proportional, the force is proportional to the acceleration. The net force is proportional to the acceleration. That means if someone push you with 300 pounds, then your acceleration will be 1g. If someone is pushing you with 150 pounds, your acceleration will be 11 miles per hour per second. Okay, so it depends on the mass. If the force is 100 pounds, then the acceleration is 1g. So your own weight means 1g, or 1g means your own weight. Okay, so if you are in a space shuttle and the space shuttle is 3g, that means there will be 3 times your own weight pushing you. So if you have a child, okay, 3 times the weight will not be as bad as someone like Peter. I don't know if he's 300 pounds. I just made this up. It could be, right? 300 pounds. Is that clear? So usually they like to compute the acceleration in terms of g, so we can compare what you feel. Like you can think of your own weight. So if you are taking off like this is bad, okay? That will be 10g. That's the most you can go. Otherwise, you're gonna pass out. 10 Gs, that will be 10 times your own weight. And the blood has a hard time to go to your brain. So too much of it, you're out of this world, right? In an airplane like this, maybe 20%, 25% G, 25% of your weight pushing you so you can reach the speed you can accelerate. Is that clear? This is in Japan. It's an old slide, so I don't know if they build another one like this, but the acceleration is like 3g. Very, very um, and friendly. I mean, if you like it, it's good. Okay, so acceleration, for example, in that case here, if you are in a rotating height, okay, you're gonna feel in your frame of reference, you're gonna be pushed on the wall. Okay, so you're gonna feel very heavy because the surface here is pushing you back. That will be your normal force. But because you push so hard on the surface, you're gonna increase static friction so much that it will be able to balance out your weight, and then they remove the floor and like you are glue. And some kids sometimes they were able to stand up, like they walk on the wall, right? Not in the US, because in the US you have over safety, but I don't know, it was in the UK or I don't know where. Not that you want to go in the UK, but anyway. So where do you think you will wait less? At the pole or at the equator? Equator, very good, right? Why? Because you see here, the linear velocity is larger. Okay, because the rotation is the same. Rotation is 1 revolution every 24 hours. But here, so here the velocity equals 0. Omega is not 0. So it's still 20. You're rotating, you are spinning. You are spinning 1 revolution per 24 hours. But in that case, you are covering more distance. So you're going to feel a centrifugal force pushing you out. And then you have the weight here pulling you in. So if you find your apparent weight, so that will be the normal force. Okay, so that will be the normal force. It will be a little bit less. So your weight will be a little bit less, but not that much. So that's why some people didn't think the Earth was rotating, because they say, oh, we will be flying off. But gravity here is very strong. Isn't that cool? Okay, so you have the linear velocity depends on the radius. That will be omega. Omega is the rate of spin. So omega will be 1 revolution in 24 hours. You have to convert that in rad per second. That will be the radius. Okay, so that will be the radius. So you see that the centripetal acceleration, we have seen that before, is v squared over r, which is r squared over omega over r, which is r omega squared. So anyway, you don't have to worry about that too much. My point is that here you will feel more of a centrifugal force pushing you out. And then someone last year who was in biology says, how does that influence uh, the biology? And I had no idea, so I asked ChatGPT. So I don't know, you can learn about it. Maybe there was some research to do, I don't know. Physiological, how much impact does it have? It's very little. Okay. Any question? Okay, so that will be redundant. So I'm not going to go into details too much because we already do a lot of things there. Just so that everything we do is for the test, right? Oh, I forgot to show you one thing. Oh, this is action reaction. That will be an example. That's a crazy, crazy workout. People who do that are literally crazy. I mean, you need so much, so much, so much muscles here. It's so hard. Action reaction. So now they cheat. Okay, they have a little motor now inside, but this is really, really crazy. And you need flat. It has to be flat, right? I will not be able to stand here. So for every action, you have a reaction. And what else? The pulley. Okay, so that's a application that I saw. You see that you have a pulley system, and 1, 2, 3, 4, it will make the load divided by 4, right? So lots of applications for pulley, and then that was cool. That's super cool. I find it super cool because if physics was taught this way, we will have more physics major. You see here, well, it's compounding, right? So here the load will be divided by 2, and then divided by 2, and then divided by 2, right? And so, but the distance here will be much larger here, multiplied by 8. Isn't that cute? So cool. So I found that super nice demo. Okay, so let's see. Okay, so Newton's applications. So this you already know how to add vectors, right? Tail to head, or you make a parallelogram. We need to find the net force. You can do tail to head. That's what it's showing you here. Tail to head. So for example, here, this is not, so just algebraically, can you find the equation? So it's not an equilibrium, not even a dynamic equilibrium. So you do have an acceleration, and now you should do it in your head. Okay, right minus left equals mass times acceleration. Quickly, once you understand how it works, you see you have an acceleration to the right. So acceleration is this way. So plus, minus, acceleration is winning. That will be the winner, right? So we can say that will be the winner, right? Is the winner. Minus left equals inertia times acceleration. So just write down an equation. So I'm going to take the x-axis here. Y-axis, I don't care because nothing good comes out of the y-axis here. I mean, it's not going anywhere. But it's accelerating to the right. So I'm taking the x-axis to the right. Okay? And the angle is the same. So it's going to be the same tension. T and T. The magnitude is the same. Okay? So what is to the right? Okay, so it will be D is the thrust. D is the engine. No, I don't know what it is. Yes, I guess it's the engine. There is something to the right. I guess it's the engine, and it's all being also being tugged. Anyone knows about that? What that will be D. Engine? Engine? Yeah, no, but here they focus on the force, right? Even if the engine is in the back, it's gonna push. So D will be the engine or the thrust, right? Pushing to the right, yes. Plus is being pulled. So 2T. So it will be the cosine. Do you agree it will be the cosine? So 2T cosine 30. So it's a free body diagram. So it's true that your engine is in the back, but something is pushing it this way. So they do a free body diagram. So you can do it also like this, right? This is the engine is pushing this way, and you have the drag this way. But they do a free body diagram, so they attach the tails to the origin. It's a good point. All agree? Okay. Loser is the friction of the air resistance, the drag. That will be, it's not well named. That will be your thrust pushing. Yeah, it's pushing. Something is pushing. maybe a swimmer who is pushing, I don't know, equals mass times acceleration. Okay, and up equals down, so it will be T1 sine 30 equals T2 sine 30. So it doesn't matter, right? It just means that T1 equals T2. Yes. Why did you add the into two T equals 30? Because they are the x component. You have the x component of T1 and the x component of T2. They are both pulling to the right. Yeah, why is it E? Like, what is E? What is it? What? Well, what is it E? What vector? D, I don't know. It's from the slide. D is the engine, is the thrust. It's something pushing the boat forward. I'm not into navigation. I don't know why you will have an engine. Maybe the engine is sick here. It doesn't work very well, so it needs additional help. Oh, I thought the boat were the what? Oh, there's a little furnace. Oh. It's being pulled to the right. D stands for drive, so it's like a thrust. It's from the engine. I don't know. Google it. Why do they need the engine plus two boats tugging? I'm sure it's in engineering something. I don't know. Do you know? I don't know. Maybe it's not. I don't know why. I don't know. It's just like, yes, look at the direction. It's something is pushing the boat forward and it's being pulled as well. And you have something opposing, which is the drag. So I'm guessing that you have some kind of engine and maybe it's not powerful enough. So they're adding tugging bolts. Maybe the wind. Maybe the wind. Maybe the wind is pushing. Something is pushing. Or the current. Could be the current as well. You're right. Maybe it's the current. Like that will make sense too. Okay, so the way they do it here, they do it the long way, but you can do that as well. And they get to the same equation. And at the end, you get the same thing. Okay? Yeah, maybe it's the current. Any question? We good? Okay, it's the most difficult part of the class. Okay, so frictional forces, we already talked about that. So the thing that you have to understand, you have static friction and kinetic friction. So you have static friction and kinetic friction. So static friction, so first of all, friction happens between two materials in contact, right? So when you have two objects in contact and one object is trying to slide between them, it's like little molecules, not the molecules, but you see the surface between here, it's not very smooth. So they're gonna hook up, right? Like little hooks. So first, it's very well hooked and it doesn't let go. So you pull, it's gonna pull back, not moving. Pull harder, it's gonna pull harder, not moving, until you reach a maximum static force, the maximum value, right? Once you overcome that maximum value, boom, then you have kinetic friction that will stay the same. It's constant, right? When it goes, it's easier to make it slide. So you pull, it's gonna pull back. You pull harder, it's gonna pull harder. So the forces are equal to each other. It's a static equilibrium. It's not getting anywhere. Once you overcome that value here, which is called the maximum static friction, then it starts to slide. And for this, we have an equation, right? So the static friction, the maximum one, will be equals to the coefficient, which is called the static coefficient. It's a constant. It depends which materials are in contact. Rubber and cement, for example, large coefficient, ice and ice, small coefficient, times the normal force, because it depends on how hard the surface is being pushed on. Okay, so once you go over that, then you go to kinetic friction, and that will be constant. Okay, is that clear? So if I push here, you see, I don't even have static friction because I'm not pushing hard. If I push really hard, the normal force is increasing because it's being pushed on more. I have so much static friction that it doesn't slide. Yeah. To make it slide, right? So even kinetic friction, you use that equation. So kinetic friction is the coefficient here times the normal force. Normal force is how hard the surface is being pushed on. Harder, more hooking. So hook up, right there, hooking very, very hard. So you see here the kinetic friction is always smaller than the static friction. The coefficient is always smaller, and it depends on the materials in contact with each other. Okay, so the static friction always smaller or equals to, but it very rarely. So if they are equal to each other, that means there is almost no transition between static and kinetic. Like you push, it's moving, but it's like only steel and Teflon. You see Teflon and Teflon, for example, you don't have static, which means you push, it moves. So, but you have a whole engineering field about studying that. So anyway, this is Mr. Dummy or Mrs. Dummy. I'm gonna push. No, I have to push. No, it doesn't want to. It doesn't like pushing today. So for the pop quiz, you will need to play with it, but if you pay attention, it's going to be easier. It's my computer doesn't want to push. It doesn't want to push today. Is it moving? No, because you have static friction. So the applied force equals to static friction. So I'm going to push harder. It's going to push back harder. So static friction is increasing, and you're going to see it's going to reach a maximum. Look. Maximum. No. Boom. Did you see that? So static friction reached 120 Newton, and now you have kinetic friction. Can you see that the kinetic friction is not changing? It's constant, right? Kinetic friction does not change. There is an acceleration because you have, and here you have kinetic friction alone. Okay, and you have a negative acceleration. The net force is negative 92. The speed decreases at a constant rate because there is a net force of negative 92. So it's not that intuitive, and I don't transform on my computer. Okay, so now if I increase the mass, I increasing the normal force. So I'm increasing the frictional force. Now I have to push. Now I am over what I was before, right? So I have to go over the static friction. I push hard, it's going to push back, push hard. Finally, I reach the maximum and the kinetic friction goes down to 184 and it will stay 184. It stays constant. You see the applied force minus the friction equals to the net force. You divide by the mass, you get the acceleration. And now it's going to decrease at a constant rate. Yeah? Now, if we remove friction, okay, if we remove friction, we still have to push because there is still a mass. So the acceleration will still be proportional to the applied force. I have to fix my computer. But there is no friction. No friction. No friction. What do you think is going to happen if I let go? It will keep moving at a constant speed along a straight line forever, ever after. So you don't need a force for something to keep moving. It wants to keep moving unless acted upon by a force, right? It's not intuitive. Okay, so a lot of application here. If you like to do rock climbing, you see the trick is you need to stand on one foot at a time. Because if you stand on one foot at a time, you're going to increase the pressure, right? You're going to have all your weight instead of having your weight on 2 feet, only one weight. By increasing the pressure, increasing your weight here, you increase the normal force. And by increasing the normal force, you increase the static friction. So you want to make sure that your center of mass is just above your foot so you can increase that pressure. Otherwise, you're gonna fall. And then you need those special, very expensive shoes to increase the coefficient of friction, and you put some powders. And then you have to push on your legs, right? Because you want to use the quads because you don't have much muscles in the arm, and then you pull with the arms. So it's if you have two books like this interlock with each other, you can do that as a demo and you try to pull. Not only it's compounding, so static friction add to static friction add to static friction, but also the book they fan out. And because they fan out, there will be a component of the normal force pushing the things together, so it's increased the static friction even more. So if you are interested, ask ChatGPT. It will explain very well. Okay, so it's very good engineering. I don't know, my computer is not very cooperative today. Okay, I don't know where we stopped here. Okay, so you have ways to find the coefficient of friction between two surfaces, and it's easy to do. What you do is, see, it doesn't want to click anymore. An external math. No, it's not too, too much work, but it's a good idea. Okay, so it's just I wanted to show you the demo. If you want to see all the math, it's called Flipping Physics. He has a YouTube channel, he has a website, he makes great GIF, simulation. So you will take an inclined plane and you're going to increase the angle until it's going to start sliding. To find the coefficient of static friction between both, so the book, whatever the material here, and the wood, okay, what you do is just you take the tangent. So the tangent 15, that's going to be your coefficient of static friction. So if you want to do a demo, you can try on your own. You can find static friction coefficient. If you want to find the kinetic friction coefficient, so then you do the same thing, but you tap, 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 tap. So you increase the angle, you increase slowly the angle, you tap, 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 until it starts to slide. And the angle will be smaller. Maybe it will be 12 degrees, right? And you take the tangent, that will be your coefficient. You can do the math. I'm not going to do the math because you can watch that video and it's in your textbook. It's interesting to do. There will be a sine somewhere and you have a cosine. Remember, because you have what's the component of the weight along the inclined plane? mg sine. The normal force is always mg cosine. And then you have the equation that the friction is the coefficient times the normal force. So if you massage and malax, you're going to get the coefficient equals to the tangent of this angle there. So the math is not hard, but you can do it in you see here, mg sine, mg cosine, that will be your static friction. You increase the angle until it's going to start sliding, and you find that the static coefficient is tangent of this angle when it starts to slide. If you want to find the kinetic, you increase, but at the same time, you tap, 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 until it starts sliding. Okay, here they show you the math. Now, you don't want to do that. Any question? Okay, we're gonna do a cool one. Okay, you have to buckle up. So you have this system here, and it's accelerating. There is no friction. There is no friction here between this block here on the table. There is no friction, but there is a friction between these two. Okay, so you have friction between the 12 and the 9, and you don't have friction here between the 9 and the table. And you have to remember that the friction depends on the normal force, and the normal force depends how hard the surface is pushed on. Harder is being pushed on, more hooking they have. So it's kind of confusing because you don't know where to start. But the first thing you want to do is, first thing, you decide the direction of the acceleration. And then that direction has to be positive. And then you decide what is the system you want to focus your attention to. Because you have two blocks here. So here you have a lot of things going on, right? So it's accelerating this way. So this is not moving, right? This is moving. This one is not going to move. Okay, but it has. So this block here has an acceleration that way. This one is moving here. And between the two here, you have some friction. You don't have friction here. So the kinetic friction 0.3, it's going to be between the 12 kilo and the 9 kilo. So some friction here, and it's accelerating. So, okay, so what is the force here? That's easy. It has to be winning. So here we know 50 Newton. Do you agree? Okay, you decide of the system. So I'm going to focus my attention to this system here. It's like a bag. The pulley doesn't matter because the pulley does not have any mass. So that will be my focus. Of course, something is going on inside, but that's not my business here. You have some tension here, and the tension is going to pull here. But I don't care. It's inside. Okay, or you can do it in two components if you want. Okay, so what are the forces here? So there's no friction here. What is it that I'm missing? So there's no friction between here and there. Static friction between both, right? You can feel, you can imagine in your head, like one is this one cannot move, this one is moving, but there's some friction. You see, it's rubbing. So you're gonna have some static friction here, here, between, which has to be smaller than that T here, okay, because that will be the winner. Okay, so now I'm focusing on this system here, right? So what is the winner? The weight, so 50 minus that kinetic friction. Do you agree? Yes? Okay, that's slowing it down. Can you imagine in your head? So kinetic friction equals inertia. So inertia will be whatever is inside the bag, which is 14. Very good. So 14 times the acceleration. Agree? Static. No, kinetic because it's moving. Did I say static? No, kinetic. Kinetic is when it's sliding. Static, it doesn't move. And here we know it's moving because there is an acceleration. So it's kinetic. Otherwise, it won't move. Could be static if this one at the top is so heavy that it will stop the other one to slide. But it's sliding, so it's kinetic. If it slides, it's kinetic. If it doesn't slide, it's static. So the static, yeah, you have two blocks on top of each other. This one cannot move, it's attached. This one move. And no, the opposite, right? So this one doesn't move, this one move. So the static friction is because this one is pushing on that one, right? So this one doesn't move, this one move. This one doesn't move, this one move, and they are hooked together, but they slide past each other. Agree? Okay, and now think about that. Now we have to find the kinetic friction, which depends on the material in contact. So it's going to be the kinetic coefficient times the normal force, right? What's the normal force? It's how much that surface is being pushed on. How much this surface here is being pushed on. The weight of the other one, very good, right? So this one is pushing on that one, pushing in, right? Pushing. So that will be the weight of the other one. Okay, we'll go back to that. It's not an easy one, but 0.3. So it's being pushed by here, the surface, but we don't care because it's along the y-axis, but it's being pushed on that one, right? Pushed on that one. How hard is being pushed on? And then, of course, there will be a reaction force, but we don't care. Agree? Okay, and then you can do the math, and you can even find the tension. We'll do that. So try to finish that problem and find the tension, because for every action you have a opposite reaction. So this 12 kilogram will be also pushed in to the right with the same force. So forces come in pair with two systems. Okay, I'll let you digest it. And but that's the first step. If you have any question,